So hello everybody. Um, so let me just wait till we share the screen. Okay. So yes. Yeah. So today we'll be discussing about pattern formation, and in particularly pattern formation will be discussed in the context of solving time-dependent PDEs. You have already solved partial differential equation um, with which was not time dependent. It was basically Laplacian equal to zero, grad square phi equal to zero with various boundary conditions. But if there are time dependent equations like the diffusion equation or some other equation, then there are some issues and it would be nice to discuss that. So whatever we are going to discuss, the formation of patterns, etc., was a contribution of Alan Turing in 1952, uh, and that has spawned a large amount of work, and that work is still continuing, solving various coupled differential equations. He did with two, but then there can be more things, and that's outside the scope of this week's discussion. But even before going ahead, let's discuss what do we mean by pattern formation. Now, suppose there is a space dependent concentration of some chemical, and this chemical in turn depends upon the concentration of some other chemical. So there's a coupled partial differential equation where with time dependent a variable being the density of one particular species, say density of b, time dependent density of b, which is again space and time dependent, and they're coupled with each other. And this leads rise to Turing patterns. So here all that I have done is search for Turing patterns, and then you basically get to see various kinds of patterns emerging, even if the concentration of these two chemicals was uniform initially in space and time. So suppose the left hand side figure is concentration of A, and there's some coupling, and it depends upon the concentration of B, which is on the right hand side. And here you see spots basically forming, which is the concentration of A is higher at some points compared to others, and that in turn affects the concentration of B and vice versa. And here you see some stripes forming, which is basically concentration of BC. Right now, depending upon the partial differential equation in question, one can have different types of patterns. For example, here you see some spirals appearing, and what is being solved is the FitzHugh-Nagumo equation, and we shall discuss it a bit later in class. And here you see various beautiful patterns emerging as solutions of nonlinear partial differential equations, right? And not only this, you can have other patterns such as this. So this is again FitzHugh-Nagumo, but yeah, so I don't know how to get this, but various patterns can form as you change parameters, which can be some field, suppose the concentration or temperature, which is dependent. But here we will be basically discussing all these emergence of patterns from more the perspective of solution of two partial differential equations, in which partial differential equations in general shall describe some background physics, a bit of which we're going to discuss. Okay, so with this context, so let's uh, focus on pattern formation. So, in terms of method, we'll be still using the finite differences method, which has already been introduced to you. And we'll be solving PDEs, partial differential equations, except that they are time dependent. In particular, we'll be focusing on reaction diffusion system. So this is just a word, a reaction diffusion system under some conditions, some choice of parameters shows pattern formation. But what do these mean? Just wait for a few minutes. So I want to emphasize that finite differences method is not the only method for solving PDEs. There are other methods like finite elements, which engineers use a lot. It's again about discretizing space and time, but one can have different mesh size, and finite elements is often used to model the flow of, say, air, wind across the suppose the airplane wings. Or it is also, suppose you put pressure on some solid and it's some internal structure, right? And then how does stress and strain uh, propagate under the implication under the application of force at a finite point in space? Or you have force and temperature which is varying about a continuum. So those, there you often do finite elements method. And one has adaptive mesh size in finite element methods, sometimes partial differential equations, especially the physicists who are looking at again solution of Navier-Stokes equation, flow, suppose, or flow of some fluid. Sometimes they take a fast Fourier transform stands FFT, and they solve the Navier-Stokes equation in Fourier space, because there it becomes an algebraic equation. And uh, then you transform it back to real space to figure out what the fluid is doing. These are other methods, but we shall stick to finite differences method for this for the class for this week. The references of whatever I say, uh, of course, is the Alan Turing paper of 1952, The Chemical Basis of Morphogenesis, where he showed how patterns can spontaneously emerge. Uh, Other things, other points where I have taken reference from is this site, www.degeneratestate.org, and so on and so forth. And some of the background physics, which we will not be discussing because we are more interested in the technique, but the background analysis of the partial differential equations of reaction diffusion systems, which when they become unstable and become uh, pattern forming, if you like, variation of density in space and time. There's some wonderful lectures by Professor Pushpa Vanam of IIT Madras, lecture number 32 and 33. You can search for Turing patterns or reaction diffusion systems, and that will provide the uh, necessary mathematical background. We'll be discussing it in very brief, but if you find this stuff interesting, I would strongly recommend you maybe after the course is over to go over the lectures of Professor Pushpavanam or any other book that you want. At least I learned it very well from here. Anyway, so coming back, so our focus, as I said already, is solving partial differential equations on the computer. This is a computational physics course. And now let's discuss what is a reaction diffusion systems. Before that, just let's look at the diffusion equation, and that looks like this. It has, suppose, phi some field, some density or temperature, whatever be it. And uh, there's a first order del phi del t. It's a first order differentiation in time, and that is equal to d. D is some constant, the diffusion constant, which basically says how quickly something spreads and become uniform over space. The diffusion constant is represented d. And I mean, if you have your Fick's law, where it basically says that the current of particle depends upon the concentration gradient of the particles, which is Fick's law, and that's basically where the diffusion constant comes from. A similar equation is also seen and known as the Fourier's law for heat transport, right? So you again get the diffusion equation, except yeah, so these will be the phi will be temperature essentially. uh, Here when we are using Fick's law, we are using a macroscopic description, right? Because in molecular dynamics, you might have figured out that we also discussed the microscopic origin for diffusion. But in Fick's law, and when you're solving this partial differential equation, you are saying, okay, the current, the flow of particle current is proportional to the gradient of the particle density, and the proportionality constant is the diffusion constant. And when you mix it with the conservation of mass, when you couple it with the conservation of mass, you essentially get the diffusion equation, right? So yeah, so basically you can also write del phi del t equal to divergence of current. At current, you write it in terms of Fick's law, and then you get this. And note that this is a double derivative in space, and this is the uh, so-called diffusion equation. And how does the diffusion equation behave? How does the solution to the diffusion equation behave? Suppose you had at initial time um, a spot of ink only at x equal to 0. So here you have to tell the initial condition, which is at time t equal to 0. You had a spot of ink only at x equal to 0. So you are specifying in time and space, because it's a partial differential equation in time and space, right? And suppose you say that, okay, you have a Dirac delta function at x equal to 0, a spot of ink. Then as due to the diffusion equation, the ink is going to spread over space as a function of time. So it is going to be spread like this. The solution of that equation is going to be phi as a function of x and t, is going to look like this. So this is a Gaussian, but the standard deviation, or rather the variance, is 2 dt in one dimension. It's 2 dt in one dimension. So the variance itself is changing as a function of time. As time increases, the variance increases. So it's a Gaussian uh, what is it called, standard deviation. The spread changes. So at a later time t, it would even more, because the variance has increased. It's 2 dt. And of course, this is a Gaussian function, and here also you have 2 sigma, which is 2 dt, and variance increases with time. And what is the message? The diffusive processes make phi being the field, like a temperature or density, and uniform. It makes it uniform at long times if there was a high concentration of phi at time t equal to 0. So once the concentration has become uniform over due to diffusion, right, there is no net gradient. There's no net change in concentration of particles as a function of space. And so the uniform concentration cannot evolve further once it has become uniform. So what is the message? Diffusion equation tries to make mm, phi, the field, uniform unless it is pushed by boundary conditions. So when you were solving the Laplacian, it's when there was no time dependence in the previous module. Then you were solving the Laplacian of the equation, and there were very strong boundary conditions. There was heat current, and which was different and along different boundaries. And in that case, of course, you have a temperature profile. But if basically the boundary condition is like goes to infinity, and phi is 0 at infinity, then as a consequence of diffusion equation, the concentration of a chemical, suppose a perfume, spread at a certain point in space, is going to spread over all the room. It will become uniform. The perfume will become uniform uh, in a closed space. Yeah, so that's the message of diffusion equation. Okay, now if you add reaction terms, and what do I mean by reaction terms? Let's think about a chemical reaction. Some oxygen interacting with, suppose, hydrogen gives water, and something else, right? So basically there was initial chemical species A and B, and A and B react and they decay and form C or D. The other hand, you can look at reaction terms in a certain broader perspective, that suppose over space, over a forest, so that's a function of x, y, z. I mean, maybe x and y if it's on the surface of the earth. Then A could represent the concentration of species of deer, and B could uh, represent the concentration of tigers. And if tiger number of tiger increases, then number of deers will decrease. Right, so on the right hand side, as, as a as a consequence of A and B interacting, you again have A and B, but the concentration of A, the deer, could decrease. And if it decreases too few a number, then the tiger won't get its food. Then the concentration of tiger will also decrease. So that's again, so those are basically kind of reaction terms, where A depends upon the concentration of B, B in turn depends upon the concentration of A, and there can be nonlinear terms, and so on and so forth. In general, the concentration of deers can be represented as the concentration of some species, in general species A, which is function of both x and t. And the concentration of tigers can be represented as the concentration of B, species B, whatever be it, chemical, tiger, whatever, because we are more interested in the solution of the partial differential equation. And that again is dependent on x and t. Now, suppose there was at a certain point in space, there was a large number of deers, then the tigers would come there. And then once they eat that up, the number of deers decreases. But at some other point in space, some other point in the forest, in the neighboring forest, maybe there might be more deers left. So then the tigers will migrate there, right? So the concentration of A and B, if you like, are changing not only as a function of time, but they're also changing as a function of space. Or if there are too many tigers at a certain point in space, then the deer might want to also migrate out, or spread out, or do something else, or distribute itself over the entire forest. So hence A and B are function of both x and t. Okay, so when one couples the diffusion equation with some reaction processes, which leads to the addition of a growth of A, or decay of A, and growth and decay of A and B are represented by del A del T, because it's changing as a function of time. But A is also a function of space. So at different points in space, it could change in different ways, right? So these are the diffusion terms, and these are the reaction terms. And similarly, you have an equation for B. So R1 is a function of A, uh, which in turn is a function of x and t, and is a function of B, which in turn is a function of x and t. And this is function R1, and this is function R2. And these are called reaction diffusion equations. And in particular, we will be discussing pattern formation using the FitzHugh-Nagumo equation. You saw some beautiful spiral patterns at the beginning of this lecture. And in the FitzHugh-Nagumo equation, uh, the way R1 and R2 is chosen is R1 is A, so del A del T. Of course, this is the diffusion term, but it basically increases with A del A del T, but then minus E cube is also there. B, if B increases, del A del T will be suppressed, and alpha is a constant parameter. And del B del T, the rate of change of B as a function of time, depends upon, of course, the diffusion equation. This is diffusion equation for species A, sorry, diffusion constant for species A. This is the diffusion constant for species B. And del B del T depends upon some constant parameter, some value of, and the difference between A and B. Okay, so if you didn't have these two terms, it's called the Fizzo-Nagumo equation, and they basically was a simplified version of 2D version of the Hodgkin-Huxley model, which is used to model neuron firing. But Okay, I don't know much about this Hodgkin-Huxley model except that it is considered to model the firing of neurons. So the electricity goes up and then comes down as various species of ion currents change and so on and so forth. So that's what it was used for. But then these terms are also added to the diffusion equation to create reaction diffusion equation, right? We are going to look at it from the perspective of not neuron firing or something, but more from the nonlinear dynamics perspective, solution of nonlinear PDEs, and look at patterns formed as a consequence of uh, these terms, the fight of these two terms, where uh, B tries to suppress A, B changes depending upon the difference of A and B. And there's also the diffusive term, which tries to make the concentration gradients of A and B smooth. Okay, so before we actually solve it, we have to discuss three aspects. One is actually the method of solving, the finite difference method, when you have a double derivative on one side of the equation and a single derivative on the other side of the equation. So this is single derivative on the other side, grad squared is a double derivative. Then before just blindly plugging in parameters and solving them, one has to check whether this your system, your finite difference scheme, is working correctly. And how do you check? uh, you check by developing an understanding of the nature of solutions and checking whether your computer code which you have written is doing what you expect it to it. Now for this expectation, you need some understanding of how these equations behave. So we're going to look at various limiting uh, terms, drop some terms and see how those equations behave. And finally, the third step is basically look at the actual solution and seeing Turing patterns. Now, we will be using the explicit finite difference method. Now, it is not one of the best method, but it is computationally, I mean, in terms of algorithm, uh, easy to implement. Now, since we're not spending a huge amount of time on this Turing patterns, we'll use this, but it has its caveats, it has its problems. There are some better methods to solve partial differential equations, and if and when you need them, you can use it. We'll very briefly discuss it. Those are much more computationally stable methods. Now, in the explicit finite difference method, del A, del T, the single derivative, can be written as A, so at time t, can be written as 1 by delta t Ax at any point, one point in space, t plus delta t and t. So the difference in the value of a at time t plus delta t and t at a certain point in space. And if you discretize it, this x will become I, because you are going to define it at discrete lattice points. We have discretized it and made it lattice points, and this is delta t. Right, this is the finite difference. This is how you would write it down. Now this grad square a, del x2, can be written as again 1 by delta x whole square. Now note, uh, this is all the same time t, but you are basically, this is the concentration, this is the value of a, sorry, this is the value of a at a lattice site to the right, lattice site to the left, and this is your mid lattice site where you are interested to calculate it, right? So that's how you'll calculate gradients. Now in 2D, now this is the original equation, the FitzHugh-Nagumo equation. Now note, here this is ing at a particular lattice site, the left hand side of the equation is t plus delta t, this is t here. On the right hand side of the equation, note, we are using the value of a at time t, because if we know the value of a at time t, then we can calculate the value of a at time t plus delta t, right? So what we are doing is writing the derivative in the x direction, double derivative in the x direction, the double derivative in the y direction. J plus 1 is the y index, I plus 1 is the x index, right? So this is something which is familiar. And so this would be the diffusion equation, the terms written in black. And if you also had the reaction terms, then you would add a at time t ij minus, for each lattice site, a t whole cube minus b t at time t ij plus alpha being a constant. And similarly, you would have another equation very similar looking for b, for the concentration of b. I mean, for the partial differential equation for b. Right now, if delta x and delta y was equal to h, and this equation would look a bit simplified. So here the you still have this term, right? But on the right hand side, basically what you have is, if you have a lattice point, I plus 1, I minus 1, j plus 1, j minus 1, right? Minus 4 ij calculated at time t, right? And now if you take this delta t here and take the h square here, then what you have is d delta t h square. Take this term to the right hand side and you get this equation, right? So here you have aij at time t, here you have aij at time t, taking it out of the brackets and collecting them, aij time at time t, you have this prefactor. And knowing all of these, if you know the value of a at neighboring lattice points at time t, then you can calculate the value of aij at the next time t plus delta t. Similarly, you can do this for each lattice site, and then you will get the value of a ij at t plus delta t for all lattice sites, and then you can calculate the value of a at any lattice site at time t plus 2 delta t, right? Because now you know the values of a at all t plus delta t, so then you can calculate for the next time. But anyway, so looking at this equation right now, now for stability, this term has to be positive, right? Else it will keep on decreasing. So this quantity has to be positive for stability of the simulation scheme, not stability of the equation, stability of the simulation scheme. So correspondingly, you can write that this has to be positive, and you can look at the how stability of these simulation schemes are calculated. Some book which I already posted. So this has to be positive or delta t. When you are solving it, you have to be always careful that the choice of your delta t is smaller than delta x whole square by 4d. Right? Delta x being h equal to delta x equal to delta y. Only if this condition is satisfied will the solution be stable. The numerical errors go as proportional to delta t and proportional to delta x whole square, because it's a second order term in delta whole square. So as I said, this is called the explicit method of finite differences method. uh, it is only stable provided this condition is satisfied. You have also the implicit method, where you write this equation as previously, the left hand side of the equation as previously, but note, to calculate a plus t plus delta t, uh, on the right hand side of the equation, instead of t, you are using the values of ai at t plus delta t, and ai minus 1 at t plus delta t, and ai at t plus delta t. But you don't have this values, right? But you can write a similar equation for each value of I, right? And this equation can be rewritten as 1 plus 2r, r being d delta t, so basically d delta t by delta x whole square, So if r is that, one can write it like this. You're just rearranging terms. Note here there is ai, here there is ai minus 1, here you have I plus 1, and you don't know the value of any of these. Ai t plus delta t, you don't know. Ai minus 1 t plus delta t, you don't know. And ai plus 1 t plus delta t, you don't know. What you know is only this. So these are three unknown variables, but you can write similar equations for each value lattice point I, right? So then this will be I minus 1, this will be I minus 2, and this will be I. So you will have a set of many such algebraic equations, and you can then solve it by the matrix method or whatever. You have basically a series of solution of these such algebraic equations, and you shall have as many equations as there are variables, and you can solve for it because you know all of this. And thereby, by suitably solving this set of algebraic equations, you shall get all the values uh, of these quantities at t plus delta t simultaneously. And once you know that, you can calculate it for t plus 2 delta t, right? So that's how you can do it. So this is a numerically stable and it has convergent solution. It is, however, it's computationally more expensive. And even for this, the error goes as o to the power delta t and delta x whole square. You have also the Crank-Nicholson scheme, which is even better, but it comes at a cost, of course, where you have the right hand side of the equation to be identical to what was before, but on the sorry, this was the left hand side of the equation, but on the right hand side of the equation, what you are doing while calculating gradients is take a mean. So ai plus 1, ai minus 1, 2 ai, that remains intact, delta x square remains intact, but you are calculating this gradient square, grad square, at time t plus delta t and at time t, and taking a mean of these two values. Right now, again, just like the previous case, you don't know the values of ai t plus delta t, and these three terms you don't know, right? But you can rewrite the equation. But just like before, you can have a series of linear equations for each lattice side. The number of variables, unknown variables, will be the same as the number of equations, and you can solve it again by some matrix method or whatever method, and then you get the values of these variables, all the variables at each lattice site at time t plus delta t, by solving this algebraic equation. And then you can again go and solve for the next time instant. So this method is called the Crank-Nicholson. This is more complicated. It will have a more computational cost because there are more terms. Now, this method is numerically stable. Again, only the first one, one can do a stability analysis, and the error goes as order of delta t whole square and delta x whole square. But we stick to the explicit method because it is simple to implement and get quick answers. But when you are serious about it, you have to know which partial differential scheme to use. Okay, so that's how you solve the equations. Now let's discuss a bit about understanding the equations. Now there were various terms in the reaction terms. Here we are first going to neglect the diffusive terms and just look, if you just had del A delta equal to alpha, right? Then what would be the solution? A would linearly increase with time, A equal to alpha t plus C, right? So that's basically what you are doing, is del A del T, ignoring all terms and looking only at when del A del T equal to alpha. Now, if you had del A del T equal to A, so ignoring diffusive term but proportional to A, then you know what the solution is. A is going to exponentially increase with time by solving this. This is going to be the solution. And this also you know. Now, suppose you keep two nonlinear terms and drop the minus b and plus alpha and also the diffusive term. So, suppose del A del t equal to a minus a cube. Then what would be the nature of the solution? Now, if a was equal to 0, say, then del A del t equal to 0. So, a is not going to change as a function of time. right? So del A del T is not going to change, equal to 0, no change, and it's called a fixed point, because if you start with A, if the concentration of A at a particular lattice site or each lattice site was 0, then it's not going to evolve, because A is going to be remain 0, because del A del T equal to 0. But suppose A at time t equal to 0 was equal to 0.1, right? Then del A del T equal to 0.1 minus 0.1 whole cube. This is a much smaller term. So it's going to increase, not exactly like this, but it is going to increase anyway, right? Because del A del T is positive. A will keep on increasing till it reaches A equal to 1. And when A equal to 1, note that these two terms are going to cancel. So del A del T again will become 0, right? Uh, and then after it reaches A equal to 1, the value of A is not going to change. It's again a fixed point, right? So as long as you start between any value just greater than 0 and less than 1, the value of A is going to flow and become equal to 1, right? Now, what would happen if A at time t equal to 0 was slightly greater than 1? Then you know that if it's suppose this is 1.2 whole cube and this is 1.2, so it would be negative. So del A del T would be negative. A would keep on decreasing, the value of A would keep on decreasing till it reaches again A equal to 1, right? Because A minus A cube is going to be a negative number when A is greater than 1, but when it reaches A equal to 1, then it's going to remain there. It's not going to evolve anymore. So basically, A equal to 1 is a stable fixed point, because once it reaches A equal to 1, a slight deviations of A, the value of A, from the value of the fixed point, A equal to 1, is going to make it flow back to A equal to 1. So it's a stable fixed point, right? Now, let's complicate a bit more. So, as I said, AT will decay to 1, and AT will remain 1 at some point in time, right? It cannot change. And similarly, if the value of A at different points in space was 1, or some value, I mean, close to 1, it is going to flow back, even if you give small deviations. That was, of course, using this equation, not the reaction diffusion equation. Okay, so this is the message. But now suppose uh, del A del T was A minus A cube plus alpha. You see, I'm slowly adding complications, right? Where A is positive. Sorry, alpha is positive. Now, you know, if A is slightly bigger than 1, this term is going to dominate over A. But alpha, A plus alpha equal to A cube, assuming alpha is a uh, small positive number. So I'm not discussing when alpha is huge, because then I don't know. But suppose the value of alpha is 0.05 or zero point 0.1 or zero point 0.2, then you know there will be some value of A where A plus alpha will be equal to A cube, right? And that will be the modified fixed point. But the question is, if you give a slight perturbation for to A about the fixed point, will it be stable? Will it flow away or come back to the fixed point? So we are discussing essentially stability of fixed points, right? How will this behave? Now, this is just one equation. Of course, later we're going to discuss coupled equations, but I need to develop an understanding of these equations, the diffusion, does the diffusion equation do? What do these terms do? And then we will go to the Turing. Okay, so at the moment, so rest of it will be in the part 2 of this lecture. So let me stop recording.